Welcome to Brain Vision.
This is quite a long problem, so let's start with part A and try to move as quickly as we can through it. So we know the distance traveled along the path is 8 meters. We know the time it takes to travel it is 4.2 seconds. We know the initial speed is 0. We don't know the acceleration, and that's what we want to solve for. So we're going to use, pin glitch there. We're going to use x minus x naught is equal to v naught t plus 1/2 acceleration times t squared. We plug in our knowns here, and we get that the acceleration along the path is 0.907 meters per second squared. Now, the free body diagram for this process is we have a normal force going up this way. We have a tension force pulling it up that way. We have a friction force pulling it this way, opposing the motion. And we have gravity pulling down that way. And we, of course, need to break the gravity up into its vertical and horizontal components according to this angle here, which we're told is 40 degrees. Now, from Newton's second law on the y, we get that the normal force is 16 to 90 newtons. And this tells us that the friction force is equal to the coefficient of kinetic friction times this. And we're given the coefficient. So multiplying that through, we get 5702 newtons. Now, Newton's second law along the ramp in the x direction, if my coordinate system is like this, so positive x is actually up the ramp in this case. So that gives tension minus force of friction minus mg sine theta is equal to mass times the acceleration that we just found, which is 0.907. This is Newton's second law along the ramp. We can solve this for the tension now that we know the friction force. And when we do that, we get that it is equal to 21,340 newtons. And now we have to look at the table and determine what size cable is safest. And we want to pick one that's able to handle tensions higher than this. And so the one I picked was 5/8, which is the first one that can have a tension higher than this. So that's the cable I'll pick, 5/8 inch. And that's the end of part A. Part B asks us to test their hypothesis that the breaking strength is proportional to the cross-sectional area. And so just repeating their hypothesis, their breaking strength, which I'm going to indicate by B and then S here, is proportional or equal to a constant times the cross-sectional area. And then the area in terms of the diameter it's the radius, which is diameter over 2, squared times pi. And so that's their hypothesis, that the breaking strength is equal to this. Now we're given a table of the diameters and the breaking strengths, so we can just plug in the diameters and see what this hypothesis tells us, and then compare them to the actual breaking strengths. And so, for instance, we can get that the breaking strength of the 1/4 inch is 0.049. I'm ignoring this constant for now. And you can do the rest of these, but really the important ones, 1/4, 1/2, I get 0.1963. And the breaking strength of 1, I get 0.785. Now, if it truly is proportional to the area, then you expect these numbers to follow a linear line. But you'll see that when we plug in 1/4, we get a really small value. 1/2 should be double that value. And it's not, it's quite a bit larger actually. We also expect 1 to yield double this value, and it's way larger. So I think their hypothesis is kind of bad. Personally, I would not validate that hypothesis. I think it's quite rough. Now, it also asks us for a good value for 9/16 inch, which is not logged in the table. And so the way I did this is I took the safe load value for 5/8, which is the value just below, or it's just above, it's just above 9/16. And then I add it to the safe load value just below, which is 1/2. And then I'm going to divide by 2. So essentially, I'm just taking the average of the values above and below 9/16. And when I do that, I get a value of 24 0.35 kilonewtons, which is what I would use for the safe load value of 9/16. So now pin's glitching out again, but we're going to do part C. And let's see, pin, come on, pin. Okay, there we go, part C. So pretty much we're repeating a lot of part A, except now the friction force is equal to mu s times the normal force. The normal force won't change, but now this will change. And when we plug in the new value, we get 10,099 newtons. Now we're going to use the same formula that we used in part A, and we're going to use this guy here, right here, except we have a different friction force because we have a different coefficient now. But whenever we do the same steps and solve for the tension, we get 25,737 newtons, which is larger than before. So having it stationary on the ramp creates larger tension in the rope supporting it. Now part D is asking if we also have to focus on the mass of the cable, does that really change things? Well, it tells us that the length of the cable is 9 meters. And the cable we're using is the 5/8 inch. My pin's just glitched out for the rest of this problem, so let me just say it in words. The cable is 9 meters long. Oh, there we go. Okay. Let's see if we, okay, yep. 9 meters is the length of the cable. And since we're using 5/8 cable, we're given the mass of the meter is 0.95 kilograms per meter there. And so we can figure out how many kilograms this cable is worth. When we multiply these out, we get 8.82 kilograms is the additional mass of the cable, which, if you recall, we're pulling masses that are on the orders of thousands of kilograms. And so this is quite negligible compared to the just mass of the load in general. And so it does not change the answer much. It's negligible. It does change the answer, but it's negligible, so we can ignore it for these really thin wires, like the 5/8. But if the wire becomes larger, then maybe this won't be negligible. But it just depends on the situation at hand. And that was a long problem, but that's the full solution. I hope I didn't leave anything out.